So we are on the right side of the figure, and on the right, the left, that explosion type of thing is typically what we call the Big Bang. We don't really think there was an explosion. That's not the right way to think about it. I don't know if there's a good way to intuitively understand what that might have looked like, but there was nothing and there was something. That's all I can say. Okay. But typically in cosmology, we call it singularity, but perfectly fine. I'm going to use Big Bang for this talk. Okay. So on the left, there's Big Bang, and we're on the right. Okay. And this is of course not to scale, but the period that has elapsed between the Big Bang to now is about 13.8 billion years. Okay. And when the universe began, of course, everything was energy. There's no such thing as matter because even particles will decompose, right? Everything is pure energy. At some point, within the first few minutes.
And apart from that, like if there is no matter, then how can
energy is radiation? You don't need
radiation. What kind of radiation? EM wave.
Yeah.
But there was photons. Then how can
photon is not matter? It's not baryonic matter.
But if we speak about EM wave, then EM wave is created by what? Like when electrons jump from one state to another, then they emit radiation. Then how can we have EM wave?
Yeah, it's not an EM wave. Okay, I will tell you that I don't know the answer to your question up to 10 raised to minus 18 seconds after the Big Bang. After 10 raised to minus 18 seconds, we know. We don't have measurements. That's a physics breakdown as we know it right now. There is no good answer. Okay. So after 10 raised to minus 18 seconds, when we start thinking of inflation, post-inflation, we have some understanding. Okay. Yeah, but I don't know the honest answer. At Big Bang, I don't know the answer to that question. Nobody knows the answer to that question. Yeah, but people are trying to find it. Yeah. Okay. So again, I've already covered the part now I mentioned about inflation. So the universe began. There was energy. We think. Okay. We can think of it as the closest people have come to putting a name to it is something called quantum fluctuations. Okay. So yeah, that is the closest term to capture what we think might be happening. Okay. But then these quantum fluctuations, we believe, expanded rapidly in a period called inflation. Again, whether or not inflation happened for sure, if it happened, what caused it, when did it last, how long it went on, for all of that, there are uncertainties. Okay. But for our current observations of the universe to match what could have happened at that surface of inflation, we think we need something called inflation. Otherwise, our understanding of our observed universe breaks down. Okay. So you have some period called inflation, and eventually within the first 3 minutes, okay, this part we have some understanding of. We did have matter, okay, in a period we call Big Bang nucleosynthesis, okay. Out of this quantum fluctuation and this energy, particles get created, okay. So you have protons, electrons, helium nuclei, and some other very trace elements of little bit of lithium and so on, and you have a lot of radiation, okay. By the way, it need not only be EM waves, it can even be heat. Okay, but then you can say vibration of atoms. I understand. Yeah. Yes, yes. We don't know. That's a valid question. It's an important question, and that is what people who work in quantum cosmology try to answer. So you should take that seriously. Yeah. So you should consider that for your thesis. Okay. So you have atoms that you have particles that are formed, which are basically ions. Okay. So that is at the within 3 minutes or few minutes of the Big Bang. Okay. Now we start our talk, okay? So as the universe gradually expands, okay, it cools down enough for these electrons to be captured by nuclei of the hydrogen and helium atoms, so basically protons and helium nuclei. And this happens over an extended period of time. It's not an instantaneous process, okay? And all of this coexists with radiation or light, okay, energy. So you can think of this as plasma with light. It's a big mixture. And gradually, after about 400,000 years after Big Bang, which is like a very small instant of time in the grand scheme of things, the first atoms start forming or have more or less completed forming.
Then before that, plasma was there.
Yes.
But plasma is like when we give gases higher energies, then it becomes plasma.
Now, I'm saying after the 3 minute mark, after 3 minutes of Big Bang, plasma is there. That much you know for sure.
There was an atom, then how can plasma?
Atoms form. No atoms. Ions are there. You need ions for plasma. You don't need atoms to break down. You can have broken down atoms and form atoms out of that, right? So plasma need not, the precondition for plasma is to not break down an atom. You need ions and energy. You have that. That exists. That's much for sure. Okay. So now you're doing the reverse process. You're cooling the plasma and atoms start forming. That's what's happening in the universe, the whole universe. It is not in a pocket in a chamber. The whole universe exists in that state. All the what we call baryonic matter in the universe exists in that state. Okay, in the state of plasma with high energy, lots of photons. And you also have something called dark matter, which for the most part of this talk, I won't even touch upon. It is relevant for some parts, I'll come to it. But there is dark matter, it is doing its own thing. Since we don't really understand it, we can't really work back the physics of what it was forming, which is why the kinds of experiments we're trying to do can help us understand the nature of dark matter. Okay. But dark matter exists and coexists with this plasma and radiation. Okay. Now, at this surface, your first atoms have more or less started forming. And by first atoms, I mean mostly hydrogen, some helium, and little bit lithium. Okay. Now, from that period, at some point, and we don't exactly know when or how, the very first stars and galaxies in the universe start to form. Okay. We don't exactly know when, we don't exactly know how, but it happens because clearly now when you look out into the sky, there are stars, there are galaxies, so they should have started forming at some point. Okay. But we know that the radiation that these stars and galaxies emit gradually reionized most of the neutral hydrogen in the universe. Okay. By that, I do not mean some cylinder of hydrogen gas in your lab. Okay. So this is hydrogen atom on cosmological scales. Okay. Cosmological scales, typically in cosmology, you talk of scales of 100 megaparsecs. For comparison, our galaxy we think is about 30 kiloparsec size. Okay, so clusters, large clusters of galaxies is the typical unit or dimension that you talk in cosmology. Okay, so on cosmological scale, the radiation from these first stars and galaxies went to reionize the hydrogen atom. Okay, so I just repeat this because this is the foundation of the talk. Then we can go to other things. No, you don't know what happens in the beginning. Then plasma, neutral atoms, stars and galaxies, no more neutral atoms, plasma again. Okay, the entire hydrogen on cosmological scales is ionized again. So we call it reionization. And then other generations of stars form, we come into the picture, and that we are here at this part. Okay. Because this is so hard to comprehend on our time scales, this is a picture that I would like you to go and look at later. Look up the cosmic calendar. Look up cosmic calendar on Google anywhere. You'll find many of this image. Okay. So if you compress the entire history of the universe into 1 year, like our 1 year, right? And you say that the universe started at the midnight of January 1st of that year. Okay, 00 hours of January 1st. All of this I talked about, atoms forming, stars forming, first stars forming happened by end of January. By February, you already have these things here. Okay. For context, solar system, sun, whatever came in September. Okay, a few billion years ago, 5 billion years ago. First life, I don't know how to define life, so it's pretty confusing, but we like dinosaurs, yeah. So 29 December is when the T-Rex existed. Humans, again, human definition is a little vague, but we go modern humans. 11:52 p.m. Like these modern humans evolved in Africa. And basically written, whatever, the kind of humanity as is recorded comes on 31st December. Oh, this is 31st December, 11:52 p.m. And yeah, we are clearly here, okay? So this is how far back we have to go to study these objects, okay? And this is the kind of, to get us appreciation of this time scale. Please go look at it, it's a nice picture, okay? So now how do we study these things, okay? The most common and the most important probe for understanding our model of the universe, when people say, oh, we have dark matter, dark energy, those kind of things, the biggest source of information for us has been something called as the cosmic microwave background radiation, or the CMB, okay? Again, if you go Google CMB, you will see a lot of plots. This is one such picture of the CMB. And you can think of this picture as a picture of the universe when those first atoms form around the same time. So this is a picture of the universe or the radiation in the universe at 380,000 years after the Big Bang. So within the in our cosmic calendar, this would have been Jan 1st, I don't know, 5 a.m. something like that. Okay, that's how far back we see this routinely now. Okay, and just a fun fact: if you have one of those old analog TV sets, if you've ever seen, and you go between stations, you see static, right? They're black and white pixels. Some of those pixels contribution comes from CMB, right? And it's like a fun fact. And there are, I think people also have experiments where they hear this as noise. Okay, so a lot of our model of the universe comes from our understanding of this picture. And you'll see that there are some cold spots and hot spots that have different spatial scales and so on. This will tell us the nature of how those quantum fluctuations were seeded at inflation, if you studied in enough detail and in polarization. So now we come to again one Q&A. Okay, I gave you that in the cosmic timeline, but do you have a sense for when exactly the first form, what they look like and all that? That's what we're going to figure out. Okay? Now, since my title of my talk was using hydrogen to study the universe, this is a bit of a giveaway. But how should we go about studying the first stars? So if you take a picture of the universe, right? If you use James Webb or something, you do a deep field, right? You stare at one patch of the sky for a very, very, very long time so that even the very faint galaxies and optical light you're able to see, you'll get a picture like this. Every single dot here, even like some fleck that looks like dust, is a galaxy in this picture. Okay? Other than this super bright thing which is Earth. Anything that has this diffraction pattern is a star in the foreground. Everything else is a galaxy. Okay, so we can do galaxy counts, we can get an understanding of how far back the galaxies are, etc. So some questions, okay? Okay, somehow that first thing keeps blocking, but I'll hide that message. Okay, so we have seen pictures from, yeah. Yeah, can you just say okay? Thank you. Perfect, thanks. Professional values. Okay. So we have built some really nice telescopes. You've seen images from some of these telescopes. We've been hearing about James Webb in the news. So let's do some quick exercise, okay? So do you know how big the mirror of James Webb is? Any guesses? Guesses fine. You don't have to know, but you can guess.
That's biggest and school bus.
School bus. So you should give me some meter, something. Okay, we'll take 20. Fine, why not? We'll just take some numbers. Okay. Any other guesses?
15.
Oh, 15, 20. Okay. Again, because James Webb is bigger than Hubble space is lesser than that. Any number for Hubble? Because this was that previous best.
Around 8, 9.
15, 8, 9. Okay. Okay. You don't have to get it right, but you can guess some numbers because remember, this is something you've flown in space. Okay, so there are some limits on what you can fly in space, how big it can be and stuff. Okay. So what is the farthest James Webb has seen? Like how far in, like?
Around 10 to 14.
10 to 14. That's a wide range. You can give some number.
12.
12. Okay, fine. Any more numbers? 14. Okay. Any more?
I think more older than even the galaxy age of our universe, like more even far. Because I had heard that even we have found galaxies older than universe size. And space that we have to look even beyond that. Huh?
Okay. No, you finish your sentence.
When the galaxy started forming, maybe.
Okay, so galaxies say 13.8 billion years old. So
We're talking like
you can say redshift or age. Redshift, if you know what redshift is, or in terms of age of like how young the universe was, the universe was 100 million years old then, or from our side, we have seen 13.5 billion years away. That's also
5 billion years.
okay. Fine. Okay, done. Then how far do we need to go in either units to study the first stars that I talked about? In my cosmic calendar, I showed you Jan 31st or February 1st. So do you get a sense of how early that is in years?
Around 20.
20? Okay.
20, 30.
Okay. How, if you want to build something like a James Webb or a Hubble to study those first stars, how big should that mirror be?
We can do the radio.
That's because you know the title of my talk. But okay, but we can do this exercise, right? Fine. So how deep, if you want to go that deep, it has to be clearly bigger than James Webb, according to my number, except yours because you think we're seeing beyond the age of the universe. But okay, no problem. No guesses? No? Okay. So what is the largest optical telescope we have on the ground? Because clearly we can put things in the ground bigger than we can fly in space for practical reasons, right? So do you have the number of how big an optical telescope we can do on ground?
Actually, there are something.
Okay.
I don't know the exact figure of
There's one more coming up next slide. So I'm going to give you the answers now. So James Webb is 6.5 meters. Hubble is 2.4 meters, and we still saw quite deep. James Webb is 14.2. I think now it's 14.3. Okay, it's a significant difference, but okay. Around 30, but 20 is also acceptable because our models of realization are different. Okay, 30 we have to go. We need about 100-meter mirror in space to be able to do this. On Earth, that number is 39 meters, 40 meters. Sorry about that. About 40 meters. Okay, so even on Earth, to build an optical telescope with a 40-meter mirror in segments is extremely complicated, very difficult. We don't know if we'll be able to do it the right way. And we have to do 100-meter, I guess, in space to look at those pulsars. So let us say it's impractical. Okay, it's not impossible. It's impractical to try to use optical to study the first stars and galaxies. So hence we use radio. And in radio, you have plenty of this in a full dedicated talk.
Number like what exactly is the
Okay, I'll come to redshift. So 14.2 is a unit called redshift. Okay. So in cosmology, redshift corresponds to the age of the universe or distance from us. Okay. So redshift 0 is where you are. Okay. And redshift of 1100 is, for example, the CMB surface you see. It's not a linear scale. It's the age of the universe mapping to redshift is not a linear scale. It depends upon your model of the universe, how the universe expands and so. Okay. But for the purposes of this, when the universe was 300 million years old, okay. So if we are 13.8 billion years old, 13.5 billion years from us, we have been able to detect with James James Webb. But we have to go even further to detect the very first stars. Okay, right. So again, please tell me if you have any questions specific that has not been covered. I don't know how much detail people have gone in, so we can talk about it. So we want to use, instead of using optical light from these first stars and galaxies, which is very impractical, like we discussed, we want to use a radio emission, not from those stars and galaxies, but from the hydrogen in the universe as these galaxies form and evolve. Okay, so galaxies form out of this gas, stars form out of this gas. Okay, because hydrogen collapsing into like that spheroid, burning hydrogen to become helium is what a star is. So hydrogen in the universe plays a big role in these stars and galaxies. But we're going to use a radio emission from neutral hydrogen to interpret our understanding of these first star galaxies and the universe when these first stars and galaxies form. Okay. What the 21 centimeter signal is, quick recap. Hydrogen has one electron, one proton. The electron and proton can have their spins aligned or anti-aligned. The anti-aligned state is energetically a more favorable state, so it likes being in that state. So naturally, the hydrogen atom will have an electron flip from the aligned to anti-aligned state as a function of time. It takes like few million years or something like that. It's not a very common occurrence. But because our universe is so old and the hydrogen atoms are so abundant, our universe can be bright in hydrogen. Okay. So we want to use, and the photon that comes out in this energy difference has a rest frequency of 1420 megahertz, 1.4 gigahertz, corresponding to a wavelength of 21 centimeter. So now, if the hydrogen in the universe at a certain point in time emits a photon with a wavelength 21 centimeter, it's coming to you after a long time. Okay? And here is where we have something called redshift. Please tell me if it was extensively covered in cosmology yesterday. I don't know. Okay. So you can think of, you've all heard of the Doppler effect. right? Doppler effect, you've done problems, relative velocity and all that, okay? That happens because your source and observer are moving with respect to each other and you have some dilation, some frequency gets stretched or compressed or whatever, and you have that standard, whistle and trail example, right? I hope you know what I'm talking about. So in this case, you have something similar, but it is not relative motion because we're all in the universe and we're not moving with respect to the universe. Even though our galaxy and solar system is moving with respect to the galaxy, we won't get into that. But in general, our universe itself is expanding. The what we call as the fabric of space-time, okay, which in cosmology we call metric, it's itself expanding. So a better example for this is to think of this balloon and have some pattern in a balloon, okay, like a small sine wave with a certain frequency. As I blow air into the balloon and it expands, this sine wave gets stretched out. There is a sine wave here in the same color, so you can't see it, but it is there. So you can look at the blue and the red, for example. The frequency of this sine wave has reduced, or the wavelength has got stretched out as the balloon expands. So this is the most useful analogy to think of what happens to radiation in our universe as well. Photons are emitted or light waves are emitted, right? And as the universe expands, by the time it reaches you, the universe is expanded. So the light reaches you at a different wavelength or frequency than when it was emitted. And that change is always in the direction of reducing the frequency or increasing the wavelength. Okay, suddenly if something starts compressing, you may see something in the reverse direction. We've never witnessed that yet. Okay? So this quantity of how far back you're looking in time or how much this wavelength has stretched is called redshift. Okay. So like I mentioned, right now we are at a redshift of 0. Okay. Redshift of 1 is half the way to the beginning of the universe. It's not a linear scale. Okay. It's like a logarithmic type of a scale. Okay. So this is the formula for getting the relation between wavelength and redshift. Okay. And you can change this to frequency also. Just invert the lambda. So the 21 centimeter signal from neutral hydrogen that was emitted way back when the first stars and galaxies formed, okay, will reach us now not at 21 centimeter anymore. Or 1.4 gigahertz was emitted at some point from hydrogen atoms in the early universe. Today they reach you at lower frequencies. Okay, how low frequency depends upon how far back in redshift you are trying to study. Okay, so there are the signal we are trying to detect that comes from hydrogen in the universe when the first stars and galaxies form is very, very weak. Okay, very faint. I will show you some plots and amplitudes. But what we are trying to do now is we think we should be looking at a frequency range of about 100 megahertz or correspondingly a wavelength of few meters to be able to look at neutral hydrogen signal that was redshifted to us from a range of redshift, because we don't exactly know when the first stars and galaxies form. Okay, we don't have an exact redshift. There's a whole range of redshift. So we look for a range of frequencies and we try to detect the signal. Okay, so this is what we do in our research field.
Can you give the range in numbers?
I will show you soon. Okay, so this, like I said, some examples. This signal, you can look at it in two ways. You can look at a certain patch of the sky and look at just in that patch of the sky as a function of frequency or correspondingly redshift, some amplitude of this neutral hydrogen. Or you can study the universe as a whole, okay, and assume that the entire universe had hydrogen in it. The average hydrogen evolves as a function of time when the first stars form, first galaxies form, when those sources go supernovae, right? The average amplitude of this 21 centimeter signal from the universe will change as a function of time or frequency in our case, right? So you can think of it as a global signal. Global as in all directions. It's not like one point source that I have to look at that direction of the sky to study this. No, I look at the entire sky because hydrogen is everywhere. Okay. It's redshifted to us, comes to a low frequency range. It's a very, very weak signal. I'll give you examples of how in radio astronomy, we keep converting between, we don't talk of it as power, we use a unit called Jansky, but most convenient for us, we use something called temperature, or it's an equivalent temperature. Okay. So just for example, over a frequency range of 1 megahertz, if the signal is 10 millikelvin, that corresponds to a power of 10 raised to minus 19 watts. Okay, and we want to measure such a signal. We want to measure signals of typical amplitude 10 millikelvin or minus 10 raised to minus 19 watts with our receivers. When clearly our experiments will see a lot of power from all kinds of other sources. So this signal that I'm talking to you about now from the first stars and galaxies has never been detected by anybody in the world. Okay, this is an open problem in cosmology. There are a few groups across the world who are working on this, including our group. Okay. Right. So here is that answer to some of those questions. Let me know if it's getting too intense. I'll back off. But again, this is the same picture I showed you, but looking at it in a little bit more detail. This is up to 1 billion years. Okay. So we are way off this chart. Okay. So, and again, Big Bang is there. First, we don't know what's going on, but starting at 10 million, the Big Bang is off the plot as well. So here is when we think interesting things start happening. Okay, so age of the universe is about 10 million, and redshift is about 160. Okay, and we are ending this plot at a redshift of about 6.5, and age of the universe is 1 billion years after from the Big Bang side. Okay. This is just one model of what we think could have happened, and I'll explain this model to you a little bit detail. Here, what we think is going on when we see this. Okay, what we're looking at here is the gas in the universe, the hydrogen in the universe. Okay, so here everything is uniform and at a certain temperature. Here things are starting to clump together. Here some clump things are getting hot. Okay, so this is called the temperature of the gas. Okay. What you're looking at here, and this you can think of as if you're able to get a 3D view of the universe. Okay. If I collapse this 3D view into just amplitude, okay, across the sky, I just collapse. I don't want the spatial information. I don't want the fluctuation. I just want the average information. That is this plot here. Okay. Y-axis on this plot, you see temperature going in negative units in Kelvin, which is not physical. So what this is a differential temperature. I have the temperature of this 21 centimeter signal, let us say from the universe. I'm looking at the 21 centimeter amplitude in contrast against the light or the radiation from the universe, which is for us the cosmic microwave background. Okay, because this 21 centimeter is just one photon among many other sources of radiation. The most dominant source of radiation in the universe is the cosmic microwave background at these redshifts. Okay. So if I look at the contrast of my 21 centimeter and the radiation from CME, this is the contrast. Okay. So let's look at what's going on. So here you think nothing is happening in the gas, right? Or and the spatial scale you can't really say anything. Everything looks uniform. What we think is happening is the dark matter halos or dark matter, which we have not talked about so far, is something that does not have a radiative component. It's not radiating light, but it has mass. Okay, it is gravitationally it can interact. So dark matter, I guess particles, because we don't exactly know what it is, starts clumping together, and you have these huge structures that we call dark matter halos. Okay, which is like a gravitational potential well. Okay, the hydrogen gas is what I want to call baryonic matter. Okay, will start falling into these potential wells. Okay. That's what's happening when you start seeing the clumping. Here, what you're seeing is that the temperature of hydrogen, okay, is slowly starting to cool faster than the background radiation. Okay, because matter and gas have different thermodynamic properties. Matter and light have different thermodynamic properties. Matter cools faster than radiation. Okay, so this is just matter cooling down, and gradually, you start forming the first galaxies when you start seeing these clumpy structures. Okay, you don't see it in the resolution here, but once you start forming these first galaxies, at this point here, right, these first stars and galaxies start going supernovae. They start exploding. They start having violent deaths. Okay. When they explode, they also emit their own additional energy, such as X-ray photons, right? The X-ray photons, okay, start heating the gas again, okay? And the gas temperature start going above the radiation temperature. So it goes positive, right? So here it's hot gas, right? And eventually you start ionizing the gas because of heating. Okay, you give a high energy photon to neutral gas, it will start getting ionized. Gradually you run out of the ionized gas. Neutral gas. You run out of neutral gas and 21 centimeter no longer exists. You don't have 21 centimeters from the universe on average. Okay, so that is what this picture is. And this is a typical generic model with some assumptions of, oh, this is when the first galaxy is formed. This is when the heating would begin. This is how much it would be the gas. But all of this is an unknown. This is just one model. So we want to go out and make a measurement of the signal to then interpret and answer when did the first stars form, how did they form, what kind of radiation did they emit, how much radiation did they emit. Right? So this is what we're trying to answer. Okay. So this is one example of what these signals could look like in practice. Okay. I've just zoomed in on one frequency range. This is 55 to 200 megahertz. 50 to 200 megahertz. And what curve I showed you previously was the black one. Okay, but the black one need not be the only curve. Any of these or something in between, something outside this curve, be the real 21 centimeter signal we're trying to get from the very first stars and galaxies. The amplitude on the y-axis is in Kelvin units, so let's say millikelvin. The brightest it can go in magnitude is about 250 millikelvin as per standard models. Okay, and I told you 10 millikelvin is like 10 raised to minus 19 watts. So at the most, you get an order of magnitude improvement. 10 raised to minus 18 watts. But it's still a very, very, very weak signal. Okay. This is a kind of an analogy. This is to be taken very, very lightly, like with a pinch of salt, because we're not trying to look for acoustic waves. But an example is you are trying to find a very, very weak ripple. Okay. To think of a stationary lake, there are some stone has fallen, it creates ripples. Okay. So your stone in our case is the star. Star has formed. And the ripple that it has created is the hydrogen signal. It has disturbed the hydrogen environment in the overall gas. Okay. The surface of the lake is very flat and clean. And you see the ripples, you can study the ripples and make some estimations of what is the size of the stone, where did it fall, how high where did it fall from. Right? You can say something. So we want to deduce similar things. We want to understand the properties of the first stars and galaxies by looking for hydrogen, and we can do that in an ideal universe. You want to now try to find this ripple and study that stone by looking at an environment like this. Okay. I'm just trying to tell you this is a very, very, very noisy and difficult problem. So now I'm going to give you this as your data and tell you, tell me about that stone. Okay. So this is the kind of problem we deal with, and this is why the signal has never been detected before. Okay. So, okay. The kinds of things we want to, the kind of challenges we deal with when we try to do these experiments are, first of all, even though the signal, like I said, is very faint, the first major problem we will see, even if we were the most ideal, we had the best data, ideal experiment, everything is perfect, there is no interference, is that our own galaxy at these frequencies is very, very bright in radio. Okay. Our galaxy has cosmic rays and electrons. There are magnetic fields in our galaxy, and these electrons get accelerated along those magnetic field lines to create what is called synchrotron radiation. Okay. At these frequencies where we are trying to detect the 21 centimeter redshifted signal, where its amplitude we think is, 10 or 100 millikelvin, our galaxy can be up to at least 1 million Kelvin bright. Okay, so already a dynamic range of your problem that you want to detect a very, very weak signal is large, because you have 1 part per million type of detection you have to do. Okay, and there is no way, you cannot say I will go outside my galaxy and make this measurement, because we don't know how to do that yet. Okay, at the most we've gone a little bit outside our solar system after decades and decades. So this is not possible for us to step out of our galaxy to make this measurement. Okay, so we have to live with our galactic emission and figure out a way to separate the signal from the 21 centimeter and our galaxy's radiation. Okay. The other kinds of things you will see are these bright lines, which is, I guess you know what this is. Anyone know what this is? RSI, right? Radio frequency interference. Okay. So just to give you a sense, this slope that you see here, the baseline slope, this comes because of our galactic emission. Okay. And all these individual lines you're seeing comes from radio frequency interference. Sometimes the existence of this alpha itself can change the shape of this baseline. Like around these, you will see something will get lifted. Okay, just because that's how receivers work. Will saturate things and will start misbehaving. Okay, so this slide thanks to sort of who we talked yesterday, but you have way back when cosmic microwave background. Dark ages is the period I told you when the dark matter halos start forming. That's called dark ages because the gas is doing something interesting, but the stars have not yet formed. So you don't have radiation from the stars coming there to us in optical. So that period is called dark ages. The period when the first stars forms called cosmic dawn, and the period when the gas reionizes again is called reionization. Yeah. So this is the dark ages when no sources have formed yet, but it is starting to collect the gas. This is the cosmic dawn, when the first stars and galaxies are formed. And this is the epoch of reionization. Okay, for all these, we can use 21 centimeter. For reionization, for these redshifts, we can also start using some other probes. People have tried to use X-ray radiation. You can try to use things like James Webb and so on. But you can't really do anything beyond certain arbitrary redshift this speed. You definitely can do this only with redshift. Okay. Oh, already? Oh, that's nice. Okay, I will write it. Okay. Alright. So the kinds of things we will learn when we make these measurements are when the first stars formed, how efficient the star formation process was, how efficient the radiation from the star formation stars were to reionize, how big the dark matter, all of these are open problems in cosmology. As much as we don't know about inflation, we don't know about this. Okay, this period of surrounding dark ages, cosmic and inflation are the two big pieces of the puzzle in standard cosmology. Okay, we understand as little about this as we understand about inflation and vice versa. Okay, so I've shown you this before. These are kinds of signals that could exist that we want to detect in the galaxy really, really bright. I have done this. Okay, so typically what an experiment would look like that is trying to detect this signal. You have an antenna, you have some receiver electronics, you collect the data and analyze it. Okay. The antenna, if you're not from you don't need an engineering background, basically you know what an antenna is. It has a radiation pattern like a beam, it collects, it's a sensor. You have to do, you cannot connect your sensor directly to a computer. You have to do some processing. You have to amplify the signal. You have to do something called calibration, which tells us if I receive this much signal from the sky, it will show up as this many units in my data. That's calibration, right? And in the process, you should also remove the parts of the data that comes from your own receiver. Okay. And then you look at your data, right? So this is a typical experiment. There are many experiments that have been trying to do this for a while. Our favorite experiment, because it is our experiment, is called SARAS here, and that is SARAS 3. So SARAS has gone through many iterations, many generations. So SARAS 4 is now taking data in the Arctic, which is why sort of when others are there with SARAS 4. But yeah, SARAS 3 floats on a lake. The other experiments, and I talk about this a bit more, this is EDGES, mostly from the US, but sits in Australia. This is REACH, sits in South Africa, but led by UK. Rhino, I think, from South Africa, UK, Rhino, Australia maybe. MIST, again, is a Canadian experiment sitting somewhere in South America. GINA is an experiment in Australia, and there are a few others. Okay, so about a handful of experiments that all look relatively simple. So it's not a complicated, not many antennas. It's not an array. Much like the horn you will see outside and you do 21 centimeter. It is a very nicely designed antenna with some nice electronics, and you're going to collect data. Okay. Then comes, I'm going to show you some more SARAS pictures because it's very nice. So SARAS has gone all over the world. So this is SARAS, I think, in Andaman. This is SARAS here in Gauribadhanur. This is the very first edition of SARAS. If you walk out to the field, there's some empty patch where there's no grass and trees. That is where SARAS first took data and got some nice results. These two are SARAS different editions in Ladakh. This is SARAS in about maybe 100 kilometers from here near Anantapur. Okay, that also got some really exciting results. Okay, so this is a very much home experiment. And now Saras is taking data in the Arctic. Okay. So, like I said, these are the kinds of signals that we think are possible from theory. Okay, so clearly, just as the experimentalists are going to try and detect the signal, there are many groups of people who are doing theoretical modeling of the signal. That's what tells us these curves, right? They put into their simulations gas physics, cosmology, star formation processes. There are 6-7 parameters that they vary, and they give us a prediction of this is what your signal could look like. So then when we collect our data, we try to match which signal that looks like from the simulation. Okay, that's what those are methods. So these are all some standard signals predicted by simulations. This is what an experiment called EDGES, like I showed you, detected, which clearly looks nothing like the standard signals. Okay. So after this, Saras has taken data and has shown that the signal is not real. Okay. Because if the signal is a real signal, if it is a real cosmological signal, any experiment that has a sensitivity to see it should see it, right? Because it's a global signal. There's nothing special about the location where I just took its data, which was in Australia. Anywhere in the world, if you build a good enough experiment and have enough sensitivity, if the signal is sitting in your data, you do your data processing correctly, you should be able to see it. Cyrus did not see it, okay? So definitely we have confirmed that this is not a cosmological signal, but EDGES stands by the result saying we always see it in our data. One possibility is that data analysis, there could be some issue, or there could be some systematics. Systematics are types of noise that do not average down with time. They're not Gaussian noise. So there is some artifact in their data, either from receiver or something. So the only way we can counter this is some third experiment should come out and measure and see, do you also see or do you also don't see? And such an experiment has not yet come to that level of sensitivity. Okay, the people have tried. So this band is very interesting because the signal is detected around 78 megahertz. So 55 to 110 megahertz, the band many people are zooming their experiments in to get the sensitivity. Okay, so if this was true, if this was a real cosmological signal, then things are very exciting because at least physics or cosmology, or as we understand it, breaks down. Okay, you either need something to increase your background radiation, because the amplitude of the signal is a function of the contrast of 21 centimeter background radiation. You need a new background in addition to the CMB, something exotic, injecting radio photons and those redshifts, okay, in your cosmological model, or you need to cool your 21 centimeter signal lower by quite an amount. So people have tried to invoke dark matter that interacts radiatively, okay, which we don't think, by definition of dark matter, we don't think it's true, but we don't know dark matter. We could have exotic dark matter that does this, that cools matter. Okay, so it's still an active field of study among theorists and of course experimentalists who are trying to confirm or reject the detection. So just we won't get into this, but this is to show you what the raw data from EDGES look like, and after smoothing it to make it look nice in that plot, that's what I showed you. The amplitude there is about 500 millikelvin. Not only is the amplitude high, the shape is really weird. It looks like a bucket rather than like a smooth Gaussian. Okay, so these are all the models that have been ruled out by Saras so far. Saras 3 has ruled out all these class of signals. Saras 2, which was about 100 kilometers from here, like I said, near Anandpur, has ruled out all of these. Okay, so it's easier to rule out than to detect in this field, because you have sensitivity, and things you don't have sensitivity to, you can't make any tweaks. So if I have sensitivity to detect this amplitude or this amplitude and I don't see it in my data, I can say this model is not correct. But we were the first to place constraints, astrophysical constraints on any reionization and cosmic dawn set of models. So this was like a world first type of rejection, not a discount. Okay, so this is what a practical experiment looks like. The ideal experiment had none of this messiness, but a practical experiment is really messy, which is why this is a very hard thing to do and why this has not been confidently detected ever. So I won't go into a lot of details, but I'll just highlight 3 things, which is, we can't see the colors here. Okay, the things that are not highlighted in pink. Okay, so your ionosphere can do things like it can change the direction in which you're actually looking at the sky. So even though the signal you're trying to detect comes from all over the sky and you don't care about it, our galaxy looks different to us in different direction of the sky. Okay? So you can be looking today at the galactic plane, so that Milky Way band. Okay, you could be looking at that, or you could be looking away from that. Just like in optical, even radio has features in the galaxy. So if your direction in which you look at the sky changes as a function of frequency, it gets very hard to separate which part of the data comes from galaxy and which part comes from the cosmological signal. Okay, you want to have that separation. So it's ideal for you to be always looking at the same part of the sky as a function of frequency. But ionosphere can refract. So it can change the direction as a function of frequency, right? The other thing that can happen is you have a lot of RFI, right? Radio frequency interference. That's problem I hope you are able to understand and appreciate from that part. And the third thing, which doesn't get discussed as often, is you make an antenna or you build an experiment that is very, very sensitive. It has it checks off all the boxes, right? But then this works well in simulation. This works well even in a lab. But when you take your antenna that is beautifully designed and go place it in a surface in the field conditions are something you cannot control. Okay? I can tell you things that when the antenna goes and sits in bodybuilding, for example, we have a different antenna property. Okay, antenna properties could be the beam of the antenna. It could be how the signal from the antenna enters the receiver. There's a function of frequency, right? Like a transfer function. That changes on a day like today versus if I pour water around my antenna, it will change. If it rains, it changes. If I put a tree there, it changes. If I put a stone here, it changes. Because we have designed this experiment to detect something that is 1 part per million. If water properties do change our antenna properties better than 1 part per million, we see it like 1 part per 1,000 or 1 part per 10,000. Then the antenna you carefully design to be perfect to 1 part per million is still a perfect antenna. It's seeing things you don't want it to see. But you also want it to be that sensitive to see far back. Okay. So you don't want to be in a medium that will contaminate or change the properties in ways you can barely measure. Because some of these measurements we can actually do. Otherwise, it just shows up in our data and we have to guess, oh, this would have been an antenna effect. So you want your antenna in a controlled environment, which is why Saras moved from land to water. Okay. On land, you can have stratification in the soil, different layers of the soil at different depths, rocks, pebbles, trees, all of that shows up in your data. Water is more homogeneous. Okay. Ideally, you'd like to go to space, free space, where there's nothing around you and your antenna behaves the way it's supposed to in simulation and some measure. Okay. So the most ideal location we think for such an experiment is the far side of the moon. The side of the moon you never see, that face of the moon. So there have been low frequency experiments way back in the 60s and 50s that show that the far side of the moon is radio quiet. So whenever this orbiter came towards the Earth, you see things are noisy. When it goes behind the moon blocks RFI. So things get quiet. So there again, this is what the far side of the moon looks like if you take an image. And you can see there are very few craters. It looks different. Okay. So keeping this in mind, we have proposed an experiment called Pratush to ISRO. And we've got some funding for Pratush to do some lab studies, which we have completed. And we don't yet have a launch date. Don't ask me if I know you will spread the word. But we are trying to get a launch. Okay. So this is what Pratush would do. It will be a dedicated spacecraft trying to detect the signal, orbiting the moon. When it goes on the far side of the moon, in both the shadow of the Earth and the sun, when it is truly radio quiet, we will collect scientific data. When we come back towards the Earth, we will downlink the data. And we're hoping that we'll have a mission life of 2 years. So 2 years in orbit, so that we'll get enough time in that radio quiet window to make confident detection. And this will hopefully truly be a confident detection because all those systematics that I mentioned that are Earth or environment dependent, we would have sorted out. And to our great advantage, we have a fantastic experiment like Saras operating on Earth. So both the experiments get the same type of detection. Then it's a solid detection. Okay. And that's what we're trying for. So this is what it looks like a toy model. So you have the gray stuff is the antenna. It sits right on top of the electronics, which is a big problem. I'll come to that. But everything is miniaturized and self-contained and it should be able to take it. And yeah, I won't go into these details. Just to give you a sense of scale, this is like someone of my height holding it up. So this is like, yeah, the size of the antenna is like this big, few meters, like about a meter. Yeah, you have a question. Okay. So the size of the antenna is always related to its wavelength, it's proportional. So lower wavelength or longer wavelength, bigger the antenna. Okay, higher wavelength, you can shorter wavelength, higher frequency, smaller the antenna. So this size of this antenna is something we cannot compress, even though ISRO asks, can you make it small? No, we cannot make it small. Our signal is at this wavelength, our antenna has to work well at that wavelength. Okay. Yeah, let me know if you want to know more details about how we figure out why we want this design and all that. But I think there are more interesting things. Okay. Just for information, I see you're doing some Raspberry Pi based experiment. So the master controller for what we have in the lab model of Pratush is a Raspberry Pi. We have demonstrated that using a Raspberry Pi, an experiment that needs the sensitivity of Pratush Saras, we are able to control and get data of that quality just with the Raspberry Pi. So the humble Raspberry Pi don't take it lightly, it can be very powerful. Okay. But again, I'll just quickly show you the core of this is of course the antenna. Then there's a digital electronics which has like a FPGA board that's called, I don't know if someone's going to talk about it, but this is like called a field programmable gate array. It's basically a bunch of logic gates that you can program and you can make adders, multipliers, you can create a logic system out of that when you program it. And here is the analog electronics that does a lot of the hard work of calibrating your data to the necessary sensitivity you need for precision. Yeah, so this is our Raspberry Pi only Pratush. And so we have to do certain things like we put our own electronics inside a box that contains the noise from our electronics. So we do all of this and go to the far side of the moon. But if we are generating our own radio frequency interference, then there's no point. We'll never see the signal, right? You can't carry your RFI with you. So we have been putting in a lot of effort to block or reduce the RFI by putting our electronics in what we call EMI enclosures, electromagnetic interference shielding enclosures. We have a solution for the ground, but it's very heavy. We don't want to be launching something like that. So we are trying to work with other people, material scientists and so on to see if we can make this lighter. Okay, but
is it reason to make the downside of the antenna parabolic and make electronics?
Yes. So, like I said, the antenna has two properties. One property is the beam of the antenna, which is for sure, which directions we are sensitive to. Okay. And we want the beam of the antenna to be as stable as possible with frequency. So here there are a bunch of colors. Each of this is a different frequency. To our requirement, we think it's stable. The other property of the antenna that I didn't discuss so much about is how the voltage or the signal from the antenna enters your receiver. We call this return loss. Okay. So again, we want that to be small as a function of frequency. Okay. If this had like a ripple or some shape here, then we want to know if the ripple or the shape we are seeing in our data is coming from our antenna or from the signal that looks like a ripple. So we want to keep this as smooth as possible, this as steady as possible. To achieve that, we had to do some fine tuning and shaping. This shape helps keep this thing smooth. If I made this flat, for example, because it's nicer if it's flat for practical reasons, that shape changes. My return loss becomes unacceptable. So it's a combination of these two factors that give us this final shape here.
So will you take the data in a circular block like containing it for like these two blocks just showing here and not the center data?
Yeah, it's not. So basically, this antenna, if this is the pole, right? This antenna is blind in this direction. So if I have some bright point source here, I'll never see it. Its maximum sensitivity is towards the horizon. So that is where I'll have. So, but the signal I'm looking for comes from everywhere. So it doesn't matter. So I have to just make sure that I take enough data and I have, that's all I care.
So you will get signal from everywhere, like the same signal.
Same signal. The cosmological signal comes from everywhere. That's the advantage of this. So I don't need a narrow pointed beam. I can have a big beam, but I need to know what else is coming. Right? If the sun is there, I need to know. If our galactic plane is there, I need to know. That we do in modeling. That we as long as I know what direction of the sky I'm looking at, I can put this beam model and figure out what else my antenna will see. The cosmological signal, the one we want to detect, comes to us in equal amplitude from all directions of the sky. No problem.
So how do we figure out which direction in the particular signals?
So the cosmological signal that has no direction at all. It comes from everywhere. Right? You're sitting in a room filled with the same signal in all directions. Anywhere you see, you'll see. Other things, right? We have, I don't think I have pictured right. We have like maps of the galaxy, okay, that we have made, where we know in this direction of the galaxy, there is something there. In the other direction, something is not there. So we have a model, okay, we know that from other data. Which direction of the sky my instrument is pointing to, right? That our satellite will tell us. There will be some star sensor, something that will tell us our coordinates of where we are looking.
Like how we do 3D mapping with the help of horn antenna and
Something like that, yeah. Yeah, but for that, we don't need our antenna to do it. Other experiments have done it. But we just need to know, this is, I'm looking northeast. I need to know that. If in northeast, what and all my galaxy will emit, we can figure out. And we'll see that in the field.
What is the return loss? What kind of return loss is considered to be good for?
Oh, very good question, because we want a very bad return loss. A traditional antenna has a good or a very well matched return loss. Okay, so for those who know return loss, it is okay. Let's say ratio of voltage that comes into the one that goes out, like a reflection. Okay. The better matched an antenna is, you will see something like a resonance or something like that, and the typical good values are minus 10 dB, 20 dB, etc. If we match our antenna, if it's a well matched antenna within our band, you will see a resonance which is a shape. We don't like the shape. So we always operate our antenna off resonance. So the resonance frequency for our antenna could be some 200 megahertz, but we operate from 55 to 110. So for our case, this number could be from minus like 3 to minus 7. That's okay. It's a poorly matched antenna because we prioritize shape over amplitude. Okay. But our galaxy is very, very bright. So even if it's poorly matched, we get enough signal from our galaxy. The cosmological signal is weak. So its amplitude will reduce, but we'll still be sensitive to it if we collect enough duration in time. So we prioritize the shape of return loss over the amplitude. But if somehow magically we're able to make an antenna with minus 20 dB return loss over the full band and smooth, we're very happy. We don't know how to do that. Very difficult.
So basically, to make it wide band,
Wide bands.
we compromise on the.
Exactly. But we think we can live with this return loss, even though it's poor, because amplitude is something you can build with time. Noise you can reduce with time. If it's a systematic, if it's a shape in your return loss, no matter what you do, it will not go away. We never detect this. More questions?
still don't understand why we are prioritizing the shape.
Oh, okay, good. This is why. This is what your galactic radiation will look like. This is what the signal looks like. So in your data, because this is so weak, what you'll see is just this. You'll see something like this. Okay. From this, you have to extract this. Okay. Mathematically, one way to do it is to fit like a curve, like a power law, and say anything that has a smooth shape like this is my foreground or galaxy. Something that is left behind, which is not smooth, is my cosmological signal. If both of these were not smooth, and this will become not smooth if my receiver is not smooth, like no shapes are there in my return loss. If I mess this up and make this also like a wiggle, there's no way I can separate these two. We don't know of a way to separate galactic signal from the cosmological signal other than the shape.
How does the S11 parameter affect the shape of
like this. So if I have the S11 I showed you, the smooth S11, this becomes like this. Okay, this is the sky spectrum, galactic spectrum, will become like this with that smooth S11. There's still some shape, but we still think these two can be distinguished. Imagine now this becomes like this, for example. These are a very wiggly S11. This could become like this. Right now I have to separate this and this. Very difficult. So S11 modulates the input sky spectrum by its function. It's this multiplicator function. So your this sky will become like this. That's why.
But then the sensitivity will reduce.
Will reduce. So we can build sensitivity with a system like this by just taking data for longer time.
But can you go back to the slide of RAWS curves plotting?
Yeah.
Again, pages.
The red and maroon, that one. This one?
I want to know the RAWS curves are the curves plotted or
The maroon-
similar.
No. The maroon ones are the curves Saras has not seen. In the sense, we know these are not the real curves. No, measured. We have measured that it's not there. We can do that. So, okay, the gray ones are all the simulated ones that are only simulated, but we don't know whether or not they are real. We don't know if they are the correct curve. The maroon and these maroon ones also, in that sense, simulated, but they are simulated and taken data. And Saras has said confidently that these are not the correct models for cosmic dot reality.
Data of what? Because we didn't detect any cosmological results.
That's right. So you don't have to make a detection result. You can also have a rejection result. These are called constraints. So you take data, and let us say you do some magic one. Okay, I know my experiment well enough to say that if this signal was there, I would have detected it. That much again, I know from the way I've designed my experiment.
So the prior data you just compare.
No, I have an experiment. I've taken data. I have done all the process of removing RFI in my data. I have removed the galactic contribution in my data. What should be left behind is the signal that I want to detect. The signal is not there. It's not there in my data. Okay, I've checked and I've taken the data. Let's give an example. Okay, very bad example. I can't think of anything. Okay, I'll give you a bucket of white balls. I'm going to tell you or not, that's a pink ball in this. You take out all the white balls, you see no pink ball, you say no pink ball. That's all it says. I've taken out all the white balls in my data. The pink ball is supposed to be there. These are those pink balls. It's not there in my data. So I've rejected, I've confirmed that the universe, whatever 21 centimeter signal the universe gives me, it could be any of these. Only one is true. But I know these are not true. So we will look in various action.
Regarding the very good tip.
Yeah.
About this. We interpret that it might be from the the instrumentation side, right?
Yeah, instrumentation or data
Here it's
analysis.
supposed to be with very low temperature.
Yes, very.
Then how
no,
can
this is not very low. It's very bright. Don't look at this negative side. Think of it as magnitude. The deeper it is, brighter the magnitude is.
But we interpret that the gas is so cold.
Yeah, that is an interpretation, but this is signal amplitude. But okay, continue your question. Sorry.
That was my question.
Yeah.
Because if my interpret it's very a very low temperature.
Yeah.
How can instrument give that low temperature solution?
So think of this. The closer it is to zero, the weaker this will. Okay. This is just amplitude. I can flip this and say, oh, if I show you the same plot in positive direction, you will see this is the brightest signal. Right. So this magnitude as negative. Don't think of it as weaker and weaker. It is not. The closer to it, zero it is, the weaker the signal is. Take the absolute value of this y-axis. So anything below this is hotter. So if I draw a dashed line, I say Saras has a sensitivity of here. Okay. Anything more than this on this side, I know I should be able to see. Okay. So for understand in terms of sensitivity, flip this curve to positive axis.
But instrumentations, they do give this.
Yeah, they can. It's very hard to build an instrument that does not give a dip.
Then coming to the particular curve model,
Yeah.
then how will you differentiate the instrumentation dip from the cosmological dip?
That's why we spend a lot of time in the lab doing these tests. So one is in our receiver, we make sure that before we go to a field, before we go to Gauribignor or Arctic or Andaman, we take our receiver and connect different things to the receiver in the lab. We don't even connect it to sky.
So like particular curve, you do the fitting for the dips.
Yeah. So we check. No, we don't fit to the dip. I come to that. You want? Okay. I can discuss that. I'll come to that. It takes some time. You have another.
You were talking about like rejecting of those lines. Let's say, coming to your example again, let's say remove all the interferences and stuff, and you concluded that like those red lines which was supposed to be existed, but it's not there.
Yeah.
What about those gray areas? Like, is it present or like it's
Yeah,
not?
so these are not yet ruled out. They're still valid. They're still valid. So in the yeah, don't worry about that example. That was just to tell you how we can reject things in data. Okay, but that means all of these were possibilities. These possibilities are ruled out. These possibilities are still there, and one of them could be correct.
Ma'am, how did we did the like what was the physics of predicting these shapes?
Yeah, I'm not an expert, but I'll tell you what I know. So people write different types of codes. It's not coding, okay, but coding that codes physics. Okay, people write numerical and what they call semi-numerical codes where they simulate the universe on large scales. In the simulation, they put in different cosmological parameters. Okay, rate of expansion, how much baryon density, how much dark matter, dark energy, etc. They put in different some parameters. What we call parameters in the simulation are things like redshift of star formation efficiency, a virial mass of the dark matter halo. So they have some astrophysical and cosmological parameters in the simulation, and they run the simulation. Okay, it's very expensive, computationally expensive to run these simulations. Okay, and for entire range of parameters, for every permutation combination, they get one curve. Okay, so for one value of star formation efficiency, there are sometimes there are other bounds. For example, you can let this go wild. You can go 0 to infinity, for example. But from CMB, from cosmic microwave background, from other studies such as say JWST, etc., you put in like definitely some star had already formed at that redshift, right? So you put some bounds, okay, and you say that definitely we think from other studies reionization ended by redshift 6. So you have some limits on all these parameters. So when you have like 5-6 parameters, you can have so many 6 factorial versions of the curve. So every single curve here is one permutation combination of those 6 parameters that you pick. That's how they do simulate.
It's not that the data from the edge
Yeah.
which gave that deep
Yeah,
shade,
yeah.
was it like not predicted?
No, it was not predicted. So this, when the result came out, the first thing people realized was none of the standard, because all of this we call standard physics. Dark matter does not interact radially with matter. This is radiation background amplitude at this much. All of these are knowns. So now you have to change your physics, the simulation parameters, to be able to explain this if this is real. Which is why people can now, then you can start putting what we call exotic physics. Things like some annihilating particles, some things I don't understand, but like that is a whole field of study. You can get a range of other predictions. But now this is theory trying to explain an observation in that direction. It was never predicted.
But this was not predicted. How did Saras predicted this one?
Oh, Saras did this after edges.
Okay.
So edges made a detection.
Similar to the edges.
Yeah, so edges first claimed the detection in 2018. So 2019, Saras customized the experiment to be sensitive only to the signal. Okay, this was done before. They don't look at these curves, only this. Okay. So edges made a detection here, this amplitude, okay, like this. Okay. So Saras built Saras 3. Saras became Saras 3 floating on water. To have, if this was there, we should be able to see it. It was custom designed to go and test if the edges signal is real or not. But here we should see it in our data also. Okay? And we didn't see it, and we had sensitivity up to this level. So no such shape was seen in our data till about some 280 to 60. You had another question.
I wanted to say that since we ruled out the edges,
Yeah.
like what the edges had detected,
Yeah.
so it's like the model that the physics that we are doing
Yeah.
with this cosmological stuff, so it's still valid, so we don't need to change it.
We think so, but there are people who there are enough people, theorists, for example, they're continuing to look at this seriously. Because right now it's 1:1. One data point says signal is there, one data point says signal is not there. This is more fun to do a lot of exotic, exciting things. So there are a lot of papers that have come out and continue to come out even after Saras's rejection. that, oh, if this was there, this will explain edges. So that's still happening. Yeah. But yeah, one more rejection, maybe those number of those discussions will reduce.
Deionization happens due to that 40-20 difference, huh?
No, but okay, I'll answer that.
If,
So
if that were true, then if that radiation has been used up to deionized, then how we are detecting?
1420 is not the thing that causes reionization. Reionization is caused by X-ray photons. So when a star explodes, it's a very violent process. It will emit radiation at all wavelengths, including X-ray. So X-ray photons are very energetic, okay, and they can heat the gas. You can just like IR, you think of heating, right? X-ray energies heat up the gas, which means H1, neutral gas that was emitting 1420 becomes a electron and a proton atom. So you have split the hydrogen atom that was giving you 1420 into an electron and proton. Now it's ionized. It will not give you 1420. So that 1420 signal amplitude will reduce because thing that is giving you the 1420 is now disappeared.
So for Saras also we're using a smooth S1
Yes.
So for all
No,
21 centimeter.
No. Only we, at least to my knowledge, we are the first group to prioritize this smooth return loss as much as we have. Now other groups also doing it. They're also at each, I'll be very honest, every experiment has its own design philosophy. Okay. We have prioritized beam stability a lot more than HS, for example. But every experiment thinks they have their own bias. They think they are doing the right thing. So we have our biases. Our bias has been to prioritize the smoothness and the beam stability the most. But other experiments may have their own philosophy. So self-consistency in the final result across experiments is the final whatever nail in the coffin. We have also done joint data analysis with the Edges data. So Edges team was kind enough to give us their data. Their data is public, by the way, but they gave us slightly more raw data that we could compare with our data and see if something is something interesting is there. It was not there.
So this dip could also be due to where S11 parameter being given to one particular frequency the best.
Possibly, but that's unlikely because they have an S11 measurement in their data set. Because all of these are standard things. Right now, I mean, there are enough papers speculating either it's an analysis thing or an instrument thing. One possibility is their antenna beam is changing as a function of frequency is one strong theory. Okay, so I spoke to you about Pratush and I spoke to you about things very quickly. This is what we've been doing in the lab. So we put together without the antenna. So someone was asking me, how do we know that shape is not there in our receiver or something? I think that was a question. So in the lab, before we go to even the field, like before we even collect data from the sky, we take our receiver, we connect our receiver to what we call a termination, which is basically some input we know very well. And we looked at the data and we make sure that the data is basically just noisy at the level that we want. So we have reached 3.4 millikelvin sensitivity in our receiver. I'm sure there are some shapes, but there is no sine wave, there is no big ripple and all that. This I can tell you is FM band. Okay, so because even though we have connected everything, we still see FM in our data. But for the most part, we know that our receiver is sensitive and does not have shapes that we don't like. So then we say our receiver is okay. Then we do separate tests on antenna and say antenna is okay. Then we connect everything and say both are okay. And only then we look at the data analysis for the size. Okay. Okay, I'll quickly answer the question. How do we know something is smooth or not smooth or something like that? So we are putting a lot of work in our lab in the mathematics of understanding smoothness. We have come up with functions or like curves to fit to only the smooth part in the data and reject or remove or leave behind the not smooth part in the data. Program. Yeah. So we have, as humans, we look at something smooth and we know intuitively it's smooth, right? But mathematically, we have to code this, where to write a function. So we have such functions and we use that to separate the smooth and non-smooth part. And that is how we have removed, this is basically what is left behind when we fit our receiver data with a smooth function. So if there's something non-smooth in our receiver behavior, it will show up here. but it's not there. So we think our receiver is smooth and we have qualified our receiver. So this took about 45 nights, literally nights in the lab to run, thanks to Narendra who has done this. So he has collected data over 45 8-hour nights. So night, switch on the receiver, collect data, morning switch off, charge the batteries.
So for
45.
receiver, there's a different flow for antenna. You put a
Yes,
different
yes,
flow.
yes, yes. And then the combined curve
So
is what has to be acceptable,
So
which
then
we
you
have.
cannot get the instrumentation different.
Yes. Okay. So anyway, so this is what we expect our sensitivity to be with this data. There could always be surprises. So we think if we put SARAS only in Earth orbit and we have RFI, because Earth will see RFI, right? You have satellite orbiting Earth will see RFI from Earth. So if you have some RFI in your data, we think we can be sensitive to these blue curves. If you go to the far side of the moon, red plus blue. Basically everything in the standard curve we should be sensitive to is the prediction. I won't go into this, but okay. So what we've started doing is we've started building a mini Pratush, okay, that's being led by Bharat, where we could, it's right now it's called Pratush 0, where we are thinking about putting a small payload which will not have the sensitivity to millikelvin, but sensitivity to understand the radio environment to a certain, maybe not 1 part per million, but 1 part per thousand. Okay, just as a demo, and we learn something about the environment around Earth or around the moon at this frequency. Okay, so I'll stop with this part and I'll quickly finish in like 5 minutes other part. So all of these, starting from 22, 25, okay, some of these have slipped in timeline, are all the different experiments that are going to go to the far side of the moon. Most of these are radio experiments trying to do dark ages cosmology, so lower frequency than Pratush that I mentioned. They can do things like exoplanetary studies, but many of them are also like other NASA, ESA, whatever missions. This is from throughout the world. Okay, so it's going to get very, very busy and hence also noisy on the far side of the moon very soon. And right now there is no international governing body regulating. You can transmit at this frequency or to keep things clean. So this is right now to us the most radio quiet place accessible to humankind is the far side, but may not be for too long. Within the scientific community, we're trying to be like, please don't transmit, please don't transmit. Okay, of course, I'm saying it very colloquially, but there is some mutual agreement that we have to keep things as radio quiet and clean as possible, but we don't know how things will evolve. Okay, so I finished the big part of the talk. The very small part, just to give you a glimpse, because it's not 21 centimeter, but still hydrogen. Okay, because the first atoms are hydrogen. Okay, we should be using hydrogen signal to study those first atoms or the universe when those first atoms form. So very quickly, that is like somewhere here in this period. Okay, when everything was ionized, and then gradually as the universe expands, it cools down. And as it cools, it's favorable for the proton and electron to combine to form an atom. Okay,
So we're looking past the CMB.
yes,
Oh,
yeah.
that is possible.
Yes. Because we'll discuss later because okay. All right. So I'll just zoom in a bit more. So just to explain what this curve is, just focus on the black curve. Okay. You have hydrogen and helium. Initially, everything is in the ionized state. Okay. And you have, let's take an example of a hydrogen atom. Okay. You have a proton and an electron, and you have radiation. Okay. You have photons. If your temperature of the universe or the radiation bath is too high, okay, you have very energetic photons. Let us say a proton captures an electron to the ground state. It becomes a hydrogen. For a moment, it becomes a hydrogen atom. Because there are enough photons and high energy photons, it can excite this electron and knock it off. It can ionize it again. Okay. So you cannot have this instantaneous electron atom formation. Sorry, okay. You have to have the universe cool enough and the interaction cross section between the exciting photon and your electron low enough for the electron to remain in any shell. Okay. So the way this is thought to happen is your electron first gets captured in whatever is the most outermost shell. Okay. Technically, it can go up to infinity, but let's say infinity -1. and the universe and it doesn't get knocked off because the universe has expanded, temperature is reduced, interaction cross section is also reduced. Then after again some more expansion, cooling, it will take you to the next state and the lower state and the lower state, and finally at some point it will come to the ground state, and you have one neutral hydrogen atom. Okay. And remember that if the universe is also dense, right? Right now we talked about only one electron, proton, and some photons. If you have multiple hydrogen atoms close by, any photon that comes out of one atom can knock off the electron in that state from a neighboring atom. Okay, so this is a very long, sustained process where eventually your hydrogen, the electron in your hydrogen atom and correspondingly 2 electrons in your helium atom trickle down from the uppermost to the lowermost state. But every time this happens, right, a photon is emitted. So these photons that are emitted by the process of the formation of the first atoms, this period is called recombination. By the recombination of the first atom, must exist in the universe even today because where will they go? And they are there. So this curve, black curve, is the prediction of the amplitude of these photons as a function of frequency, okay, that have got added to the CMB spectrum, cosmic microwave background photons. These get added by the formation of the first atoms because electrons trickle down from upper to lower space. Okay. So if I just zoom in between 1 to 7 gigahertz, this is what that signal looks like. Okay. This we think is like a hydrogen alpha transition between some shell 16 to 15, 15 to 14. Okay. Each of this is a N alpha line, and the amplitude is some tens of nanokelvins. Okay. We have not detected the 100 millikelvin cosmic dawn signal. Just I'm reminding you. This is 3 orders of magnitude weaker. And so this frequency range goes all the way from 100 megahertz to 1 terahertz. But we have done some studies to think that the 2 to 4 or 2 to 6 gigahertz is the ideal frequency range to try to detect these signals from the ground. From space, it changes because it's getting brighter. But we want to do a ground-based experiment. It's a very, very difficult long-term experiment where you need hundreds of telescopes with cryogenically cooled receivers to get the enough sensitivity. But we're trying it. We started with our first receiver. So we call this experiment Apsara. So we've done our own custom antenna designs. And because this frequency is higher, the antenna is really small. Like I didn't bring it, but I can it's like this big, a little bigger.
What are we actually doing?
So when I talk about the surface of glass scattering, right? What that is telling you is that a CMB photon, that by the way, it's not one instant, there's a depth to it, there's a width to it, okay?
According to this light, because like light is 400,000.
Yes.
It's beyond that.
Because our universe, like this is 400,000 years old. So when all of these atoms form, it could be when the age of the universe about 10,000 years old. The process starts then. It starts finishing here. The process of the formation of the first atoms starts finishing here. Okay. So I'll explain to you a bit more what this surface means. We call it the surface of glass scattering, which means that if there's a lot of plasma, right? If matter is in an ionized state, light will bounce off of it just by these interactions. It will not escape. When most of the plasma has become neutral matter, the photons no longer bounce off of or scatter off of them the same way. Okay. So then finally the radiation that is bouncing around within this plasma becomes free to escape and come towards us. Because the first atoms have started more or less formed by this stage, the CMB free streams towards us. That's why this surface is here. If the process of formation of first atoms was completed even earlier, this would have shifted to the left. Okay. So there is a connection. But just because we make a map of the CMB at the surface doesn't mean we can't see behind it. We can't take photos behind it. We can't make images. Okay. What changes from this? What happens here is, assume you're a CMB photon. You have bounced off of some atom. Okay. We call this process Thomson scattering. It's inelastic scattering. Direction changes. So the direction from which that photon has come to us is fixed there. After that, it's not bouncing off of anything else. So for one last time, the CMB photon has bounced off of something and comes to us. So when you make an image, direction matters, right? Whether it came from here or there, then finally the sum of all of that gives you one image, right? I'm not making an image here. I'm looking at the spectrum of the CMB. Spectrum is how much power is there at what frequency. Okay. And that gets determined at a redshift of 1 million. Like, I don't know, somewhere there, I can't remember, somewhere there. At that point, the CMB spectrum becomes a black body spectrum. I think many of you know what a black body is. So if you go and look up CMB, you will see a black body spectrum measurement of the CMB. That was made with an accuracy of 1 part per 100,000. But these signals that we want to detect is at 1 part per billion. So if you make an even more sensitive measurement of the CMB spectrum, you will see it. And that's not limited by where that photon scattered out of. I just need to know total number of photons per frequency. Doesn't matter what direction it will. So it's not it's not limited by the surface of glass scattering. So I will see beyond.
So we're studying the CMB only.
CMB in
in a-
spectral. Yeah.
Yes, in a different form.
Yes. So we're studying the CMB in a different form, but specifically we're studying the photons that get added to the CMB by hydrogen. Did I answer your question? Okay, so that's it. So pretty much, so we have been doing a lot of work around this. We made our own antennas. We are making our own very complicated looking receivers, which we need to have higher sensitivity than Saras and Pratush for this science goal. We have also been conducting surveys of the radio frequency interference because again, there will be a problem here. It's going to be a ground-based experiment. So we are again with this, we've gone to Ladakh and different places. Oh, I thought I had a better. Okay, I had a picture of Narendra in the lab, but okay, you can see you. Okay. So, let's move to that. Okay, fine. Okay. So yeah, this is us taking some nice pictures when we went for our RFI survey for this experiment. So I'll stop here. I think I've gone way over time. But hopefully I've convinced you that the only way you can study the first stars in galaxies is by using hydrogen. And this hydrogen gets redshifted and its amplitude is very, very weak. And you have to build very simple but very well designed experiments to make this detection. But the environment in which we operate the experiment is critical. So one possibility is to go to the far side of the moon. But definitely ground-based is a possibility for cosmic dawn and realization. For dark ages, the very low frequencies, you cannot do it from Earth. You have to go to space because our ionosphere blocks radiation from outside the Earth at below about 15-20 megahertz. So for dark ages, you have to go to the far side of the moon. And we can also study the first atoms by looking at the photons they emit. But again, very, very weak amplitude. Yes.
Fine. Hydrogen emits like 21 centimeter, right? But then by the time it reaches with us, it will be around like in meters, like
Yeah.
0.5 meters.
Yeah.
Then how do we get to know it was from hydrogen itself?
Only from these shapes, only from this kind of modeling.
Are we that sure that those shapes cannot be formed by like any other RFI?
RFI, no. I mean, RFI can't have that shape. But we know that those shapes are not formed by other astrophysical and cosmological processes. But our instrument can do it. That's why we take a lot of care in making sure the instrument is, at least to our knowledge, does not do this stuff. But instrument is the only thing that can do these shapes for whatever reason. But other astrophysical processes, other radiation from our galaxies, or other galaxies cannot do this.
So it cannot be a frequency of any other atom like that.
No. So I just for some information, we do spectral line studies in radio routinely. The broadest spectral lines also, like if you see our 21 centimeter curves, you'll be seeing, right? There is a shape, right? It has some width, etc. So that broadening is not sufficient to create such a broad shape in this frequency range at that amplitude. No, we are confident that if we know our instrument well enough, it's either some contribution in that is from the galaxy, some of it is from 21 centimeters. Yeah.
And it is more about the observational range limit of Pratush.
Observational.
Range limits.
Okay. So, I guess you mean like frequency in picture.
Yeah.
So, yeah, frequency of operation of Pratush will be 55 megahertz to 110 megahertz. And the reason why we prioritize this is because cosmic dawn is something we are interested in right now, in addition to other things, but we want to focus on cosmic dawn. The other reason is that this is the frequency range most contaminated by terrestrial radio frequency interference. 88 to 108 megahertz is the FM band. So that is the most bright RFI we see on Earth, and that is where we benefit the most by being blocked by the moon. And other things, we are hoping the lifetime of the mission is 2 years, and we hope to get about at least 100 plus hours of high quality data. And each orbit will get 5 minutes, 7 minutes, 10 minutes. Like that. We have to add up.
You mentioned that people things, so can you relate it to like primordial gravitational waves?
Those ripples I showed you?
Yeah.
No. I'll take the slide out of my slide deck. I always get some. So this ripple is got nothing to do with actual waves or gravitational waves. I'm just trying to make a case that you're trying to detect something very weak by looking at some other signatures. But this has got no connection to gravitational wave or primordial gravitational. And I don't think with our 21 centimeter stuff we can make we can probe those things. We can't.
So while designing the reflective side,
Yeah.
so during solar flares or some other cosmic radiation,
Yeah.
how it will affect observation?
Yeah. So solar flares, so that's why we want to operate the experiment only when we are literally in the shadow of the Earth and the Sun. So there'll be a small window every orbit where the moon is blocking both the Earth and the Sun. Okay. And we take care of diffraction effects. So because radio waves can bend around objects, taking care of all of that, we'll have a small dark patch, like a shadow. We'll observe only that. After that, we power off our electronics. We will switch off our receivers because our receivers will saturate if when it looks at the sun and so on. Beyond that, other things like cosmic ray hits and all that, like any standard space-based experiment, we use space qualified electronics. Nothing exotic.
So what are the tests you will be doing for like space and
For space. I think there is a standard test. We will work with ISRO, but we'll have vibration testing, radiation hardening testing, what is thermal testing. All of those are the standard tests, thermovac testing. So there's a standard test for any payload has to go through. Of course, we have to make sure that for it to survive the lunar environments, basically it's not a low Earth orbit, so it has to cut across a larger range of problems. So we may not be able to survive with mil-spec military grade. We have to go for truly space qualified and space grade.
Some 21 centimeter mention is basically emitted because of the spin. If two spin are up, then and will transit, then 21 centimeter emits. When you say neutral hydrogen, it emits. The neutral is electron is forced to be at n equals to 2, or it can be n equals to. Is it forced to be at n equals 1, or it can be happen in n equals to 2 or 3?
No. So in this case, it's always n is equal to 1. It's the only n is equal to 1 state spin aligned to anti-aligned gives you 1420. N is equal to 2 to 1 is what we call Lyman alpha. It's a different photon.
I was saying the potential energy both spin up, then potential energy when they spin downward,
Yeah.
that potential energy is released at H1. So it can be between proton and electron, it is nothing.
Yeah.
So electron can be at n equals to 1 or 2.
I understand.
So
No. So this 21 centimeter wavelength comes only from the hyperfine splitting of the n is equal to 1 state.
it can't be of n.
No. N is equal to 2 state is something I don't know the Zeeman splitting, whatever, very well of the other states. But if it happens, it may emit some photon like this, but it will not be a 21 centimeter. It will be some other thing. I don't know what that is.
And ma'am, some things people sometimes say angular momentum of electron.
Yeah.
If electron was a classical particle,
Yeah.
we say the spin of the surface can be greater than speed of light. That can't be possible. So we don't say the electron as a classical particle. That's why we define some quantum things.
Yeah.
But how do we define angular momentum in case of electron if it's quantum particle?
Honest answer, I don't know. I'll think about it. I don't know the answer to that question. But
You got my question.
I think I got your question. I'm not very sure. I think I got your question.
Like we can see in classical particles, that's the angular
Yeah,
momentum.
yeah.
But you are saying it can't be a classical particle doing rotation.
Yeah, no, so when I say spin, I'm not saying it's actually doing some rotation. It's not, yeah.
Then how can we define angular momentum in electron if it is not?
I think all of these, the different whatever principle, whatever quantum states and shells are purely defined as a quantum quantity. It's not, you just give it names that have come from classical counterparts. But I think you make these, you have these, like people make images of these electron clouds and so on, right? I think there, like you can make some understanding of, okay, I'll come back to this. I don't know if this is the right example, but you have like a spherical, closest example I can imagine a spherical surface. So you have a spherical surface, you can do what is called as a spherical harmonic decomposition, okay? You can take your sphere, and the sphere has like this, if your L is equal to 0, how do I do this now? You can, okay, let's say are you familiar with Fourier transforms to some extent? Okay, so I give you some arbitrary curve, there's some number, some shape. You can take a Fourier decomposition and say, I have these many modes, this sine wave of this frequency, this thing of that frequency, right? You can decompose it. I can do the same thing for a shape. I can give you a 3D surface of some arbitrary shape, okay, and take its decomposition on a spherical basis. I can say it has one sphere like this, one dipole like this, another dipole like this, right? That is how all of these electron, angular or orbital states are defined. Right? You can make that an analogy of where most of the probability distribution is, where it will sit in that shape. That is the closest analogy to from the quantum to the classical that I can think of. But in terms of angular momentum, I don't know the answer to your question. Yeah.
Regarding the status, why it is calling the global scale, right? Of course, not the spectrum, not the interferometer, something like a scale.
Yeah. So that's a very good question. I did not touch upon that, but I'm sure I have a backup slide. Give me a second. Okay, so let me show this first. And I don't know, if Prabhu's here. Let's see. Okay, so let's look at this picture very quickly. Okay, I don't have to get details, but you see that you have this matter 21 centimeter power from each pixel is changing. Okay. Now, if I, instead of taking the average picture, okay, if I took a small redshift, but I take a slice, okay, I take a slice in redshift, but as a function of space, like I have spatial information. That's what you get with an interferometer. An interferometer gives you spatial resolution. A monopolar, a single antenna thing does not give you spatial information. So if I have some spatial information, then I can make curves like this. Okay, these are called power spectrum measurements. I don't know why it's not selecting that. I have no idea. But I'll explain this to you. So you can look at an interferometer will tell you on large scales there is so much 21 centimeter emission. On small scale, there's so much 21 centimeter emission. Again, it's a Fourier transform problem. Interferometers operate on the principle of Fourier transform. But I can get at a small redshift slice in a certain patch of the sky at that redshift, how much power in 21 centimeter signal exists at different locations, not at different scales. Okay, so that is what this power spectrum is. SK is going to try to do this. There are other telescopes on ground already. LOFA doesn't do this stuff, but there's a telescope called MWA that tries to do this. There's a telescope called Hera, Giant. Okay, there are other H1 experiments that are trying to make the power spectrum measurement of H1 at different redshifts.
Because it is different from the Sarah, what is the same?
Okay. First, it gives spatial information. Saras does not give you spatial information. Okay. So if you want to know at what scales the action is happening, you need interferometer. You cannot get that from a global signal. Saras cannot give you that. But what the interferometers do not give you is okay, sure. Let's go to this. Okay. I don't know why it's not letting me do the slideshow. Oh, attention. Yeah. So interferometers give you spatial fluctuation information of at these scales there is more clumping, at another scale there is less clumping of the gas. That SARAS can never give you. What SARAS gives you that interferometers can never give you is the fluctuation. When I say the word fluctuation, you mean it's like a variation, it's like a variance. It gives you variance information, but it does not give you the mean. You need a mean about which to set your variance, right? This gives you the mean. This is the average temperature around which there is fluctuation. So they're complementary.
So the components of we both the data we can interpret with it.
Yes, for sure, yes. So there's recently, about 1 year ago, there's a paper where HERA and SARAS results were combined, and that showed that individually HERA tells you something, SARAS tells you something. HERA plus SARAS gives you extra information on which model is correct. Finally, detecting the signal is only one part of addressing the problem. From the signal, you want to be able to say something about the first star, galaxy, this universe. That is the final result. Those constraints are able to put on those parameters increases if you combine interferometer and global signal data.
Once it's right, one requires the signal related by various has needs some extra data which is for uncontrollable, right?
Yeah.
So are there any theoretical predictions for good matter?
We just
The signal is
Yeah.
unknown the radiation we are using.
Yeah,
Right?
yeah.
So are there theoretical predictions for this?
Yes,
This
yeah.
match.
Yes. So we are also looking a bit into that. But like I said, there are many ways you can create that dip. You can either cool matter or you can heat the radiation. Okay. So cooling matter, like I said, you can have some dark matter that interacts with radiation and extracts heat. It sucks away the heat and cools the gas faster. The other thing, which is this excess radiation, again, it could be, I think people have talked about annihilating dark matter. So two dark matter and anti-dark matter collide and generates photons, and that creates extra photons. So those are just two possibilities. There are many papers, but these are two broad ones. Yeah.